So today I will tell you about the joint work with Christopher Portman and Volker Schultz. The title is Quantum Proof Multi-Source Extractors in the Markov model. Okay, so I will start with a short introduction to randomness extractors and the motivation to study multi-source extractors in particular. Last QCrypt there was a very good tutorial, and also 2 years ago about randomness extractors. If you want something more thorough. Then I will explain what is the question that we are trying to solve and what is the solution that we suggest, and I will end with some open questions. Okay, so randomness extractors. So those are basically just classical functions, okay? And the goal of these functions is to start with a weak source of randomness. So here we have some classical distributions over n-bit strings, okay? And there is some mean entropy in this distribution, but it's not completely uniform, so it's not completely random. So this is a weak source. And now we would like to apply some function and transform this weak source into a strong source of randomness, which is just here this uniform distribution over a shorter string. So here we have an m-bit string, which is shorter. So m is smaller than n. Okay, and this is very relevant for many cryptographic tasks. So for example, privacy amplification is done using randomness extractors. Randomness expansion uses randomness extractors, and so on. Unfortunately, it is already quite known for a long time now that this task is impossible to achieve with just a deterministic function. Okay? For this, we can consider different solutions, and the two main solutions are the following. So first, we can use what is called seeded extractors. Okay, so here we have our weak source of randomness, but it's not alone. So we also use a short seed of randomness. Okay, so this distribution is uniform. Okay, it's a perfect seed, perfectly random, but it's very short, and it's in product with our weak source of randomness. Okay, and then seeded extractors are functions that can take the weak source of randomness and the seed and create out of it this perfect randomness. Okay, a second option is to use an independent additional source instead of a seed. Okay, so here I have the weak source that we had before, but instead of a seed, we have another weak source which is independent. Okay, so we have x and y, weak sources are independent. And a two-source extractor, for example, is a function that will take these two sources and will create, again, the uniform distribution out of them. Okay, so this option of the two-source extractor is less investigated, and we will focus on this option in this talk. Okay. So of course, we can talk about two-source extractors. We can also talk about multi-source if we have more than just two sources and they are all independent of one another. And those are needed when a seed is unavailable. Okay, so for example, in applications like randomness amplification, we assume to begin with that we don't have any perfect source of randomness, and therefore we cannot use a seed, and therefore we cannot use seeded extractors. Okay, so for these kind of applications, we really need to understand multi-source extractors. Okay. So here is the formal definition of a two-source extractor. Okay, so it's a function. Okay, from the two sources. So here we have the first source is over n1 bits, and the second source is over n2 bits, and we create out of it a uniform distribution over n bits. Okay, and we call it a k1, k2, epsilon two-source extractor if for all distribution over the sources that fulfill these conditions. Okay, so here the two sources are in product, as I mentioned, and we have sufficient mean entropy in each one of them. Okay, so it's indeed a weak source of randomness. There is some randomness in it. If these conditions hold, then the output of the extractor, okay, should be epsilon close to a uniform m-bit string. Okay, so if a function fulfills these conditions for every source that fulfill those conditions, then we call it an extractor. In addition, we can talk about strong extractors. So an extractor is said to be strong in X, for example, in the first source. If even given the first source X, the output of the extractor is epsilon close to the uniform distribution. Okay, and we can, of course, also talk about an extractor which is strong in Y. It's the same definition. Okay, so what are we trying to do in this work? So as you know, in cryptography, we care about side information that the adversary has. Okay, so in this talk, I will denote the side information of the adversary by Z. And this side information can be either classical or quantum, depending on the application that you have in mind. Okay. Now, the goal of the extractor should be the following. The extractor should output something which looks uniform. Okay, so it's epsilon close to a uniform string. Okay, even given the side information of the adversary. Okay, so even given what the adversary knows, the output should be uniform. Okay, so this is what we would like the extractor to fulfill, the two-source extractor to fulfill. And the first attempt is to allow for a general side information. Okay, so let's consider this first attempt. We have, okay, it's a function like before, and we call it a two-source extractor if for all distribution now x, y, z, now I also consider the side information, such that x and y are in product, are independent as before, and we have sufficient mean entropy even given the side information, okay? Then the output of the extractor is epsilon close to uniform given the side information, okay? And the same for strong extractor, so given the side information and the first source, for example. Okay, so this is the first attempt to define two-source extractors with a general structure of a side information. Unfortunately, this is impossible, so there are no functions that fulfill this definition. Okay, so we know by a work by Kasher and Kempe, this counterexample. Okay, so this is a very simple counterexample. If we have x, y, which are uniform n-bit strings, okay, so they have full entropy. Now we take any function, any function that we wish to prove is an extractor, and we basically give the adversary just the first bit of the output of the extractor. Okay, then in this case we have enough mean entropy, but obviously the output of the extractor is not close to uniform because the adversary has the first output of the extractor. Okay, the first bit. So what we learned from this is that two-source extractors cannot work in the presence of general side information. Okay, either in the classical case or the quantum one. Okay, so now we get finally to the question that we were trying to solve. So the question is the following. We ask under which assumptions on the structure of the sources and the side information, we must have assumptions, as I just explained, under which assumptions on the structure we actually have extractors that remain secure. Okay, so the goal is to first find a relevant quantum model for the sources and the side information. Okay, so it should be an interesting model for some reason. And then we want to show that multi-source extractors remain secure in this model, although we have the side information. Okay. So a few words about previous works. There are only 2 previous works on this topic. So the first was the one I just mentioned by Kasher and Kempe. They considered the following model. So they considered just product side information. Okay, so here we have the 2 sources are x and y. And now we have the side information is divided to Z1 and Z2. Okay, Z1 is just side information about x, and Z2 is just about y, and we have this tensor product form. Okay, and for this model, they proved that all 1-bit output extractors remain secure, even in the presence of this side information. And they also consider a specific construction of a multi-bit extractor, which basically is constructed for 1-bit extractors. Okay, so this was the first work. Then the second work is a recent one by Chang, Li, and Wu. And the model that they have is a bit different. We call it the independent leaking operation. So here what they have is that they start with this initial state, which is we have a product between the sources, and the adversary has some arbitrary state here, okay, on these 2 registers. And then there is some independent leaking operation. So this is just how we create basically the side information Z1 about x, the side information Z2 about y, and in the end, the final state of the source and the side information is this product of these 2 leaking operations. Okay, so it's a bit different, and they define the mean entropy conditions that are relevant for them. And then what they prove is that if an extractor is a strong extractor, then it is also secure in this model of quantum side information. Okay. What we do is we now suggest a different model, and we prove that under this new model, all extractors remain secure. Okay. So before I explain the model, let me go back to the definition of a 2-source extractor. Here I just wrote it in a quantum formalism, but everything is exactly the same. So now the sources, classical sources, okay, it's just written, they're written in a quantum state, okay? And what we had before was the condition that the 2 sources are independent of one another. So here we write it as a tensor product of the 2 sources, okay? Now, note that we can, if the two sources are in product, they're independent, we can also equivalently say that the mutual information between x and y is 0. Okay, with the mutual information is just this entropic quantity here. Okay, now the model that we suggest is just this natural extension. So now we consider any states rho x, y, z. So x, y are the classical weak source of randomness, and z is some quantum state. So this is the quantum side information. And what we require from these kind of states is that the mutual information of x and y given z is 0, and of course that the mean entropy is sufficiently high even given the side information. Okay, so this is just a natural extension of what I just showed you before. Okay, and then again the condition is that even given the side information of the adversary, the output of the extractor is epsilon close to uniform. Good. So we call this model the Markov model. So the model is all the states that fulfill this definition, and this definition is equivalent to saying that we have a Markov chain between x, z, and y. Okay, so this is why we call it the Markov model. This is a natural extension of product side information. Okay, so the work by Kasher and Kempe. So if you have product side information, then it trivially fulfills this definition. And I think this model is also interesting for practical applications. Well, I don't have a specific application where we already use it, but let me try to explain a little bit why I think this is interesting. So for example, consider the case where we have two quantum devices that create some weak source of randomness. Okay, now we would like to take these two devices and then use a randomness extractor in order to create perfect randomness. Okay. Now, when the experimentalists they prepare the devices, then they are, to begin with, they're independent. There is no shared entanglement between them, no correlations. But now they bring them to the lab, and both of the devices are in the same room, so they basically feel the same temperature in the room, and therefore they perhaps behave differently because of the temperature. Okay, so let's say that the devices, they are sensitive to the temperature fluctuation in a way that if the temperature is high, then they are more likely to output one bit, and if it's low, then they are more likely to output another one. Okay, so because of these temperature fluctuations, because they're in the same room, then now the two sources of randomness are not independent. So you cannot just apply a randomness extractor in the obvious way. But using this proof and this model, what I described falls exactly in this model because this side information can be thought of as the temperature. Okay, so given the temperature, if you know what the temperature of the room is, these two, the mutual information between x and y, between the two sources, is exactly 0. Okay, so I think this model should be relevant for practical applications. Okay, so let's get back to what we have. So we suggest this model, and now the question is, are there good extractors in the classical or quantum Markov model? Okay, the answer is yes. All extractors work. This is what we show. So first of all, for the classical case, we show the following theorem. So we show that all extractors work, weak or strong. So any K1, K2, epsilon, weak or strong two-source extractor is also classical proof two-source extractor in the Markov model. And here we have this loss in parameters. So now the mean entropy should be a bit higher, but this is a standard thing that happens also in seeded extractors in the classical case when we add side information. Okay, and the error should be slightly higher. Okay, but in general, all the extractors are also secure if we have a classical side information that falls into the Markov model. Then we show the same for the quantum case. Okay, so also against quantum side information that falls into the Markov model, all extractors remain secure, but now the parameters are a bit different. So the entropy is still the same as before, as in the classical case, but now the error term gets bigger in this way. So it's the square root 3 epsilon times 2 to the m minus 2, where m is the output length of the extractor. Okay, so we have a greater loss in parameters. But let me tell you, first of all, that it's actually at least as good as all of the previous constructions. Okay, so we don't get anything worse by proving that all of the extractors work in this model. And also that if you actually take some two-source extractor and you plug the parameters, you still get very good two-source extractors even in the presence of side information. So although we have this error term here, the explicit constructions are still very good. Okay. So what's more, apart from proving that all of the extractors remain secure in this model, basically prove similar results for any number of sources, okay? So not only 2-source extractor, but any number of sources. Apart from this, we also show that a bound on the smooth mean entropy rather than the mean entropy is sufficient, okay? So this is a weaker condition, okay? So you don't need to show that you have a bound on the mean entropy, but on the smooth mean entropy, and this is sufficient to apply the extractor. This is very important for practical applications because usually when one really wants to prove security and use an extractor, then what we have is a bound on the smooth mean entropy and not on the mean entropy itself. Okay, so this is very important, and it's not trivial, it's not clear also for seeded extractors, so one should do this step if you're using an extractor, but you only have bound on the smooth mean entropy. And we also give explicit constructions, okay? So if you need to use a 2-source extractor or multi-source extractor in one of your applications, then you can go to the paper and check out the parameters, and everything was calculated there. Good. So what is left to be done? So first of all, as I said, we can consider different models, and they can be relevant or interesting for different applications. Okay, and then when considering different models, we can prove that extractors work or do not work in those models. So it will be interesting to consider perhaps more general or other relevant models and show that extractors remain secure. Okay. Another interesting question is the following. So what we show is that in the Markov model, so when the mutual information between x and y given z is exactly 0, the extractors work, but it's still very interesting to see what happens if the mutual information is almost 0, not exactly 0. Okay, so this is also important for practical applications. Another question, a bit more technical, is whether our theorem is tight or not. And the same question arises also for the case of seeded extractors. So what we have is a general proof for an arbitrary extractor, and we indeed get this loss in the error of the extractor, but it's not clear whether this is necessary. Okay, so there are specific extractors for which it is possible to prove that they are secure without this loss in parameters, but for an arbitrary one, we don't know if this is necessary or not. Okay, and the final question / remark is that it's not clear what happens when the side information is super quantum, okay, and when we deal with only non-signaling adversaries. Okay, so our proof holds only for quantum and classical adversaries, but not for non-signaling adversary, and it's actually not known if there are any extractors that work in the presence of non-signaling side information. Okay, so this is important. With this I end. Thank you very much.
Thanks, Rotem. Have a question?
Let's see if I got this right. I usually think of side information as something that the bad guys will use. Mm-hmm. But here, you could have 2 extractors that are not independent, and because you use some side information, they become independent, and therefore you can extract more from it. So you use side information is used on the side of good. Did I get that right?
Well, you can think about it in 2 ways. Okay, so first, of course, we can think about it that somehow, you know, we created devices, they are a priori not correlated, but then the adversary correlates between them. And then you can think about it as an adversary. But indeed, as you say, in the example that I gave with the temperature, it's not really an adversary, it's something else. And this is correct, and I would say even more, that if an extractor works, if you have a source, and you show that the mutual information given the side information is 0, then and the extractor works. And of course, the extractor also works if there is no side information, right? This is reasonable. Okay, so now you can actually, if you have 2 sources which are somehow correlated, but you can come up with a model for some side information Z, which somehow removes the correlation, then it means that you can actually also apply the extractor when the side information is just, you know, you imagine it, it's not really there. Okay, so indeed it allows us also to extract from sources which are not, which are correlated in a very specific way.
For practical purpose, we always have only a limited size of data to decide on, to determine this independence of two sources.
Sorry, the limit size of?
I mean, we always have a certain error in the data size. I mean, we have a certain data size which causes an error in the independence determined from. So how to handle this?
Well, okay, first, I think even if you have the data, you cannot really say that the sources are independent. Okay, so even if you don't have any, I mean, you cannot prove independence of the sources from the data. This is impossible. You can always have, you know, after you finish the experiment, you will have some more information that will then show that they're not independent. So it's impossible to get to the conclusion that the sources are independent from the data. It doesn't matter if you have errors or not. So it means that the independence should really come as an assumption. It should come as an assumption from the model that you consider. Okay. Maybe one other thing that I can say is that if we think about from the point of view of Bell inequalities, okay, or self-testing results and stuff like this, then at least in the perfect case, if you have two devices, okay, for example, and you know that they can violate a Bell inequality perfectly, then from self-testing you know that you have basically pure states, and the two pure states are independent of one another. So if you think about the concept of Bell inequalities, you could somehow prove that you have independence between two different devices. But what I'm saying now is only true for the case where you have perfect violations, and then of course once it's not perfect, then it becomes very complicated. So it will not, you cannot prove that they are completely independent, but maybe only almost independent, and then it becomes tricky. So this is why the open question with the mutual information, which is almost zero, is important. But yes, in general, independence comes as an assumption and not as something that you can conclude from your data.
Okay, so thanks Rotem again for a very nice talk.